Okay, so we're doing A complement intersect B, and then we're going to turn it into either B or D, where the popular answers, which both have a big complement on the outside. So the question is, can you write something that doesn't have a complement as in terms of something that does have a complement? So it is either B or D, but which one is it? Is it the one with the union, or is it the one with the intersection? And it seems like most people picked the intersection, which is D. A intersection B complement complement. Is that correct? I didn't put in the right answer, but I'm pretty sure B is correct. I think B is correct. What do you think, Professor Humphrey?
I would definitely go for B.
B. So if you said B, if you were one of the 18 people who said B, congratulations. If you said D, then you have the little symbol in the middle. The intersection is wrong. I think the clear way to do this problem is to draw a picture. That's the clear way.
Let's draw pictures.
Let's draw a picture.
Let's draw a picture. Shall I draw a picture?
Yes, please
draw
do.
A picture. Okay, I'll draw a picture.
Live on the
so
doc cam.
let's actually, some of you may have been thinking of sort of some similar problems where it asks you what is the complement of the event, but this one said which is the equivalent to the event. And so D says is simply the complement of the event that we're trying to find the equivalence to. It's not the event itself. So anyhow, let's attack this. And I'm going to give you two solutions. One is what I call the always works way, which is that we simply shade in what we're looking for. And so there's our A, there's our B, there's our pen running out of ink. And that one's got to get thrown out at some point. And so we've got our A and our B. And then we have to say, where is A complement intersect B? Well, A complement is everything outside of A. There's B. This thing here, we should be able to label that very quickly as A complement intersect B. Now, if you took D, you said, I want the complement of that, which would be everything outside of that crescent there, that crescent moon. No, that's not what we want. What we want is the equivalent event. So how are we going to figure out an equivalent event? Well, what we want is, let's see, what are we doing? We are, well, we've got some intersections there which aren't going to work because A intersect B complement is everything outside of that area, and A intersect B complement is that area over there. That's where A intersect B complement is. I don't want that. So I'm left with two unions to look at. And so how can I think of this in terms of unions? Well, the union is where either, what is that union going to be? A complement, just a sec, where am I? A union B complement. So let's look at A union B complement. Okay, where is A union B complement? Well, there's A, and there is B complement. So I'm going to shade in my B complement. B complement, blah, blah, blah. Everything outside. And so there's everything that's got red shading is A united with B complement. But the only thing that doesn't get shaded is this section that we want, the A complement intersect B. So what we need is the complement of that union. And so your correct answer is B. Now, let's give you a quicker solution. Who likes quick solutions? Anybody in favor of quick solutions? So there's a trick or something we haven't told you before because we kind of leave it up to see if you discover it on your own. So there's something called De Morgan's laws. And there's a formal way of stating De Morgan's laws, but I'm not going to give you the formal way. I'm going to give you a solution that is incredibly efficient and easy to remember. And what this says is flip 4 boxes, all 4 boxes. So, you know, if you're not here at class, this doesn't make any sense to you. Like, it's like, you've got to kind of watch this. So here's what I'm going to do. I'm going to say we've got an event, and it's either a complement or not a complement. Okay, so that's what that little box is going to be. It's either a complement or not a complement. And then there's going to be a big box in the middle, which is either going to be a intersection or a union. Okay, so this is going to be complement or not. And that one is going to be intersection or union. And then there's a B, and it's going to have a box. And again, it's either a complement or a not. And then I'm going to go outside here, and then that one's also either a complement or a not. And what I'm saying is that with De Morgan's laws, it simply says you can flip all the boxes. So let's just flip all the boxes there. And so a complement, intersection B, if I flip all the boxes, a complement switches to a non-complement. An intersection flips to a union. A B switches to B complement. And outside I had no complement, so I add a complement. Okay? And that will work with all kinds of tricky ones. It gets very useful when you're looking at, you know, something like another example. If you had, for example, A union B complement, flip all the boxes. That's going to be A complement, intersection B, B complement goes to B, and the complement goes to there. So that's just A complement intersect B, okay? Well, I said another example, that was actually just taking our solution and working back to what we were originally asking for. So the main thing to watch is are you being asked for an equivalent event, or are you being asked for a complementary event? If you were being asked for a complementary event, then you're going to have to put a complement on all the stuff on the outside that is the equivalent event. Any questions on that one? Just think, flip all the boxes. Yep. No. It's a 2-event thing.
The thing that does work is you can do like recursion. So the thing that you can do.
Yes.
Let's try it. You can write if you what's the rule here? If you have something complement, and you have what am I trying to say? I have like f of a and g of b. This will be f of a complement union g of b complement. So in other words, the complement converts intersections into unions and vice versa. And then if you kind of like do any combination of funny things, then the complements will filter through like that. The one that Professor Humphrey showed you is the trick that works when there's 2. If there's more than 2, you have to keep putting the complement inside whatever the first thing is. So you can kind of do it like one layer at a time and work down. By the way I like to think of this is like complement is not, this thing is and so as a sentence you could say something like, what happens if you are attacked by an animal that is not, I don't know, furry and has claws? I was attacked by an animal, and was it furry and had claws? No, not furry and has claws. Well, that's the same as it was not furry or not has clause. So that's all the rule is saying, is that if you're checking kind of combinations, if you want to know if it's furry and has claws, that's a bear, right? So if you didn't get attacked by a bear, well, the animal that attacked you was either not furry or it didn't have claws.
It could have claws, though. It could have been a Komodo dragon.
Right, not furry or not has claws. So the Komodo dragon is
It's
not
still
furry.
not fun to get attacked by a Komodo dragon.
Yes, this is not fun equals fun complement. Okay, we did it. All right. There was another question here. We're good? We solved your...
There's a question back here. Yep. Question.
Yeah, that would be a fine justification, especially if you write an equation like this and then you say by De Morgan's law. That's totally legit. If you draw the picture, also totally legit. Yeah. Here, yeah. Oh, like if you had just A and someone says find A complement. Yeah, I think in general, I think that I like the way you're thinking. In a real life problem, there'll be more details about A, right? Like A will be something like you roll 3 dice and 2 of them were 7. I guess dice don't normally come with 7. You roll 3 dice and 2 of them were 1s. And then in that situation, you can further break down like what A complement is. In this problem, we were just told it's sum of n A. And so like the only thing you can have is A complement or A union and some other stuff. And the whole point of learning this kind of thing is that when there's a real life problem, you can like sort of simplify combinations of things into simpler events. So you're right that in a real life problem, there probably would be some further step. And maybe that's why it feels sort of unsatisfying to sort of write one funny set in terms of another set. But it's sort of like practice in the middle of a big problem. Yeah, great question. Anyone else? Okay.
Okay. So what we want to do today is work through a couple of the trickier practice problems and show you an attack, which, it's not like we don't want you to attack these on your own, but the point is the question is, can you find the quickest way to work them through? The first one I want to do is the Betty and Veronica game, and it also shows up something very similar in question 54, which is this idea of sports teams playing a best 2 out of 3 playoff series. Well, actually, why don't we, no, 54 is a little easier than 39 and 40. So 39 and 40's got 2 questions, so that might be the better one to do. Although they most frequently play tennis, Betty and Veronica are also keen squash players. In squash, Veronica is actually a better player than Betty and has a 60% probability of winning any game. They play a best 2 out of 3 game series. That is, the first player to win 2 games wins the series. Assume outcomes are independent between games. So then there's a couple probability questions, but what I wanted to start off with is the Venn diagram. And the reason for doing this is, in fact, we see a lot of flawed Venn diagrams with this kind of best 2 out of 3, best 3 out of 5. Of course, the Blue Jays are playing the Yankees right now in a best 3 out of 5 series, of which the Blue Jays have absolutely destroyed the Yankees for the first 2 games. And so we'll think about that. If it's best 3 out of 5, first team to win 3 games wins the series. So when we think about that, if we were doing a probability tree for a best 3 out of 5 series, do we need to put the probability through to all 5 games? Well, many will do it, but we don't need to, because once somebody wins 3, the series is over. They don't play successive games. They only play all 5 games if it's tied 2-2 after 4 games. And similarly, they only go to the 4th game if nobody's won within 3 games. So let's attack this one for questions 39 and 40. Let's get the probability tree here first. So we can think of game 1 either, and it doesn't matter who you work with, whether you want to do Veronica first or Betty first. You could say Betty wins, or Veronica wins, which of course is equivalent to Veronica loses. Okay, so you kind of just think of that because Veronica winning is the complement of Betty winning is the complement of Veronica winning. Okay, so what have we got? Veronica's got a 60% chance of winning that first game. Okay, and so Betty's got a 40% chance of winning that first game. So then we can go to a game 2. And again, either Betty wins or Veronica wins. Or again, if you want to call it B complement, that's fine. Now, in this case, these are independence between games, which is not necessarily the case. We'd have to work with conditional probabilities if, in fact, the probability of the outcome of the first game affects the probability of the outcome in the second. But in this case, they're told they're independent. So this is still 0.40 there, 0.60 there. But if Veronica wins, okay, either Betty wins or Veronica wins. And the probabilities are the same, 0.40, 0.60. Okay, so we've now gone through 2 games. And just to complete this, is a best of 3 series. Well, if Betty wins the first game and Betty wins the second game, does the series continue? That's over. It's over. So there's no need to keep putting extra branches that are kind of useless. You could make pseudo games, but it doesn't matter. Okay? So then we go to a game 3. And so if Betty wins and then Veronica wins, Betty wins, Veronica wins, well, we have to go to a game 3, and either Betty wins or Veronica wins. Okay, again, with those probabilities of 0.40, 0.60. But if Veronica won the first one and Betty won the second, yes, we're going to have to go to a third and deciding game, which either Betty wins or Veronica wins. Again, with probabilities 0.40 and 0.60. But if Veronica won the first one and Veronica won the second, the series is over. Okay? So then we can get our intersections. And this one here is going to be 0.40 times 0.40. This one here, going across here, is going to be 0.40 times 0.60 times 0.40. Oh, why didn't I give that a little more space? Let's give it a little more space. 0.60 times, oops, what did I do? 0.40. 0.40 times 0.60 times 0.40. And this branch was 0.40 times 0.60 times 0.60. And I can go through all the rest of these branches here. This one's going to be 0.60 times 0.40. I'll put a squared on that because I'm kind of lazy. And this is going to be 0.60. Well, it's got 2 0.60s, so I'll put squared times 0.40. And then this one is just 0.60 squared. Okay, so now we've considered all the different routes on that. Now, typically when you do these problems, you actually don't need to work all of that out because you pick off the branches you want. And 39 is what is the probability that Betty wins the series. Well, if I only had to answer that question, I really only have to pay attention to the branches where Betty wins the series. And Betty would win the series if we went that way, or we went this way, Or after Veronica wins the first, Betty came back and won 2 in a row. Oops, don't circle there. Don't circle there. We got to account for the fact that Veronica wins the first one.
So good thing you weren't using scissors.
Yeah, that's for sure. So what we've got there is we are going to add up this and this and this. And there's your solution. Now, the second question is question 40 is a little more challenging. Well, they're all kind of challenging, but we've got to take a look at this fact that now the series ended in 2 games. What's the probability that Veronica won? What am I looking for, you're saying?
More colors?
More colors, absolutely. Green. I wanted a green one. Here goes. Okay, if the series ends in only 2 games, well, there's only 2 ways that it ends in 2 games. It either ended here or it ended here. There's the 2 routes by which it wins in 2 games. And so if we're looking for the probability, let's just kind of take a look. Veronica won series, given series ended in 2 games. And we could attach things like A's and B's to these events if we wanted to do that, but we'll kind of just go there. And so that's going to be the probability that Veronica won the series, intersected with the series ended in 2 games. Divided by the probability the series ended in 2 games. Okay, so at this point, we could write out more stuff, but essentially what we've got is the sum of this and this gives us the probability that the series ends in 2 games, and the probability that Veronica won the series and the series ended in 2 games is simply this. So, well, why don't I use another piece of paper? That's why we got paper. So let's just take a look here. I'm going to take 0.60 squared over 0.40 squared plus 0.60 squared. That's it. What you've actually solved there is a Bayes' theorem question. But how many recognized it as a Bayes' theorem question? Did you recognize it as a Bayes' theorem question? But how many actually have already done that question and said, you got it, right? And did you know it was a Bayes' theorem question? You didn't know. See, people can do Bayes' theorem questions without knowing they're Bayes' theorem questions. So don't let the Bayes' theorem business frighten you. You intuitively can work this stuff out quite readily. So any questions on that one? Any questions on that one? Let's just take a look at question 54. A lot of variants you can ask on this kind of thing. Well, we'll leave that one with you, okay? Again, B is just a variant of this, and you attack it the same way, and hopefully you will just kind of nail it smoothly. Okay, let's look at another question I wanted to address, which is 42 and 43. So this is the kind of question that can really lock people up because there's so many possibilities going on here. You've got 4 blood types in the population. You've got different respective probabilities, and you pick 3 individuals from the population. You're dealing with a large population here, so you don't you just treat it as a with replacement case. As the probabilities don't change from individual to individual, and then you always just say to yourself, what is it I need? Let me think about the branches involved, and then I have to think about, can I actually collapse those branches? Okay, so let's do 42 first. Actually, I guess we can't do that as a mathematized.
We could do it as a mathematized.
We could do it as a
You want to do
mathematized.
42 as a mathematized?
Let's do
it.
42 as a mathematized.
Working on 42. I will open it. Okay, put in your final guesses. If you really have no idea, put in DNE or maybe /DNE to let us know. But let's see how people did. Okay. So A, B, O, A, B. The way I would do it, I draw a big probability tree. Got 4 branches in the first level, 4 branches on each of those, then 4 branches on each of those. 4 times 4 times 4. How many branches? 64 branches. That's the main thing. It takes a lot of time. Drawing 64 branches. Let's see if people are able to do it. Okay. So, so 27. If you might have mixed up and were counting things instead of doing a probability, but 30 people are in 0.027, and I think that's the correct answer. That's very good. Just over half people. Let me see. What are there some other common mistakes? Maybe some people mixed up the decimal point, or didn't try. Yeah, if you put 0.27, you just forgot a factor of 10, or 27. Same potential thing. But yeah, otherwise, nicely done by about half the class. All right. Do you want to draw the big bushy 64 leaf tree?
I really don't like wasting ink.
Oh, okay. Well, then do it on the computer.
There's a certain price to it, and there's also a price of time. So if you're thinking of all those 4 different outcomes, you got them in your brain. You got all 4 outcomes, and you got the 4 blood types. And yes, 4 times 4 times 4, 64 possible outcomes for selecting your 3 people there. That is all good. It's all correct. But let's try to simplify the problem, because we're simply asked what's the probability that all 3 are blood type O. And that allows us to collapse some categories, because as far as we're concerned, a person's either blood type O or they're not, right? They're either blood type O or they're not. And so if I just do a O versus not O, I'm down to 2 branches each time. 2 times 2 times 2 is 8. And there's really only one branch I care about, which is that I get an O, and then I get another O, and then I get a third O. And so all I need to do is go, what was the probability of a type O? 0.3, 0.3 to the 3rd power. So how many people saw that quickly? That it was just like collapse it and quickly work it through, right? That's what you want to do. You're always looking for the most efficient way of attacking a question. Now for 43, you want to do that as a mathematized
Sure,
too.
we could do 43 as mathematized. So it'll be open in 1 second. But it's what's the probability that exactly one of the 3 people is blood type O? Exactly one of the 3. That's the exactly is important. Okay, I'm gonna open it up, and we'll do it. Let me, while I'm doing that, let me put the thing on the screen. Problem 43. You're here. So yeah, put in your guesses. If you don't know, that's okay. This one, I think there is, again, multiple ways to do it. You can either do it the very long way, the sort of medium way, the super fast way. It's sort of a spectrum of different strategies. Okay, let's see how this went. Reveal counts. Okay. Most common answer, 0.441. Second most common answer does not exist. 0.441, 0.147, also popular. Ooh, this is great. Okay. what is the relationship between 0.441 and 0.147? What's the relationship between these two numbers? If you take 0.147 and you multiply by 3, you get 0.441. So in other words, there's a split in the most common answer. Some people think it's 0.147, and some people think it's 3 times 0.147, which is 0.441. Who is right? Let's start writing these out. And the different ways you can do it. I think one way is to write down a list of words like this. This was from the Betty and Veronica question. We did it as a probability tree, but you could have also written it down as words. So BBB means Betty 1, Betty 1, Betty 1, and so on. I guess in the problem we're doing with blood types, you are picking 3 people. There's either O's or not O's. So it could be O, 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 not O, O, not O, 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 not O, not O, and so on. It is kind of useful to think about writing these all out, but actually writing them all out is kind of tedious. A little bit like the tree, right? The tree we did before really was the same things. We had O, 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 not O. The probability tree and the list of sort of like words of O's and not O's are the same kind of picture. And if you spend all day writing it out, you will eventually get the right answer, but sometimes it's nice to take a little shortcut and only write down what you need. So you could write out the probability tree and then select all the ones where there's exactly one O. But if you write down the words, you'll see them right away. And there's actually, I think there should be, I claim, there are some number of words, words in quotes here. Words means 3 letters in a row, where one of the letters is not O, that have exactly one O. Exactly 1 O, and I guess exactly 2 not O's. And this is I think if you can do this little claim quickly, that is the secret to doing this problem fast. You need to know how many ways can you write down a little sequence of 3 that has exactly 1 O and exactly 2 not O's. Does anyone know the number of ways to do that? Or the number of words? Yeah. 3. It's 3. How did you get 3? Or how did you think through it? Yeah, very nice. So this one you can kind of like quickly just write them out and just think, where am I going to put my O? Where am I going to put my O? Do I put it in the middle, or do I put it in the beginning, or do I put it in the end? So there's 3 ways, and I just wrote them all out. Actually, if there were more, you could write this 3 as 3 choose 1. This is something we did when we did combinatorics, because there's 3 slots, right? There's 3 slots where the O could go, and there's 1 O that we're putting in. If there were 5 individuals and we said what are the number of ways to have exactly 2 people with O's, then it would be 5 choose 2. 5 slots, choose 2 of them. But in any case, there's 3 words like this, and so these are the 3 ways we're trying to find the probability of. There's going to be 3 branches of our probability tree, or 3 outcomes that we're counting, and each outcome has probability 0.3 times 0.7 times 0.7. So each individually is 0.3 times 0.7 times 0.7. So all the not O's are 0.7 each, not O's. And the O by itself is 0.3. So 0.3 times 0.7 times 0.7 is the probability of any individual outcome, but there are 3 outcomes that we're counting here. So the total probability is 3 times that. Is 3 times 0.3 times 0.7 times 0.7. So in other words, including the factor of 3 is needed in this problem. If you said 0.441, I will trust that this works out to 0.441, then you got it right. Any questions or comments about this one? The tricky thing is the count factor of 3. I think that's a very common mistake. And this is where the sort of counting problems can help you out and help you sort of do it in a more systematic way rather than hunting down the tree.
Question here. Yeah, so it's 0.3 probability of getting an O. So what's the probability of not getting an O? It's 0.7. It's just the combination of the A's, the B's, and the AB's. Right. As far as you're concerned, they're not O's. It doesn't matter.
That's right. Yeah, so this is a way you will eventually get the right answer if you do it with like O, A, B, O, A, B. O, B, B. Like, you will eventually get the right answer, but you're going to spend a lot of time doing it. So by sort of collapsing it down into a tree that only has 2 branches, or in other words, words that only have 2 letters, O and not O, it saves you a lot of time. Yeah, that's a great point. And that's sort of a red herring in the problem to see if you're able to sort of distill the important parts of the question that you need.
Okay, a quick hint. Give me that one on there. Not going to take this question up right now, but I kind of want to point out 45. Question 45 is typically in any kind of intro probability course, intro statistics class, a very challenging problem. Okay, very challenging problem.
Which we're looking at the litter of mice?
The litter of mice, yes. Picking that, you're doing it without replacement, etc. But try to think of the quicker way to solve this. And often the quicker way to solve something is to think of the complement, okay? The complement that there's at least one of each sex would be that they're all the same sex. And if they're all the same sex, they're either all male or they're all female. Those are easy to calculate, and then you can take those probabilities, subtract it from 1, and you've got your answer, right? And I just mentioned that question because that kind of thinking pops up in several other questions where you can get yourself into a morass if you just work it directly, but if you think complement, you can bang the answer out quite quickly. 2 quick announcements. One is my office hours, I normally do 3 to 4:30 today, but I have to be at a Senate meeting at 4 o'clock over in OVC. So I got to leave by about 10 to 4, okay? Anyhow, I will be there from 3 to 10 to 4. And on Wednesday, Professor Nika, say what's going on.
Yeah, so we'll do Wednesday where there won't be any new content. We'll make the mathematize like optional, and it'll just be review questions. I'll try to post something where you can post which questions you want me to look at on Wednesday. But if you come with questions that you want to go over, Wednesday morning, that'll help you for the exam Wednesday evening.
Strictly optional.
Yeah, optional. If you want to sleep in and that's how you prepare for your exam, that's fine with me. But in any case, we'll see you Wednesday evening for the midterm. And if you've studied, I think you'll do very well. So good luck.